How do we go through and figure this out? This becomes a more challenging question because what is this specifically looking at? Lewis structure. Lewis structure, the video that you're not supposed to have watched until tomorrow. So that could be why you're stumbling on this. Okay, but we can walk through it. I don't have any problems doing that. Because we can break down some pieces of it. We can look at it. Out of curiosity, has anybody watched that video yet? Maybe you don't want to volunteer. Just curious. Yeah? Was at least one? Okay. Okay, Lewis structure. I will say it becomes a challenging one for students to go through in nuance. You want to know why? It shows up in 130, it shows up in 151, and it shows up in OChem. Okay, that's 3 different places, which means 3 different levels of knowledge necessary to complete individual questions. Okay? Why is that particularly challenging? You go to the internet, which level of knowledge do you think the internet's going to tell you? Probably the very top. Okay? So you're going to have to run into a balance. You either use the materials you're given in this particular topic so that you're tempered to the level that you need to be, or you can reach out to the internet and hope the internet doesn't lead you astray. It absolutely, hands down, will. 100% positive on this. Right? It will lead you astray. So, first step, determine the valence electrons in POCl3. Okay, so question that I would ask, based off the lecture videos, I think we are current with being able to determine the valence electrons.
Yeah, but that's where I'm getting hung up on.
Okay, then let's go through and poke at that. How do we determine valence electrons? We want the valence electrons for this molecule. What do valence electrons reference?
The number of available ones to bond with other ones.
For what?
To create molecules.
For what thing? How are we determining the valence electrons? What are they associated with?
It's the highest energy.
Okay, highest energy electrons of what? There it is. I'm looking at a specific atom that I need to address. So in this case, I've got a molecule that has a bunch of different atoms. How many different atoms, let me change that question around. How many atoms are present in this molecule? Okay, we'll write it up bigger. Here's our atom, POCl3. How many atoms? Okay, we're getting a couple different answers here, and that's actually why I modified the question. Okay, if I said the question was how many, different atoms, you might go through and say 3, phosphorus, oxygen, chlorine. If I say how many atoms are there, you should be saying 5. Why the switch?
There's 3 chlorines.
This 3 as a subscript refers to the amount of the thing immediately in front of it. Since the thing immediately in front of it is a chlorine, we're saying there's 3 chlorines. Okay, so we have 3 chlorines, 1 phosphorus, 1 oxygen. How do I know I have 1 phosphorus and 1 oxygen and not multiple of those? There's no subscript. Well, if there's no subscript, doesn't that mean it's a 0? It has to mean it's a 1, because if it was a 0, why would I write the phosphorus? Okay, so cool. Now the question's going to come. I care about the total valence electrons, so I need to know the valence electrons per each atom. So I have to look at phosphorus, I'll have to look at oxygen, I'll have to look at chlorine. We're going to do this painfully first, I apologize, okay? Because we had a very good point of looking at the electron configuration. Okay, electron configuration is a good review thing because we should have watched that last week. We should be a little bit more comfortable with it. It's a pain, I get it. How many electrons does phosphorus have? Does a neutral phosphorus has? Okay. Where do we find that information? I only saw 2 eyes shift, which is a bit suspicious. Okay. We would have to look at the periodic table. We could find phosphorus. Do I have a giant pointy thing? How heavy is that? That's not too bad. I shouldn't drop it. We can find our phosphorus up here. Okay. We've got a 15 in the upper right-hand corner. We've got a 3097 in the lower left-hand, and we got the P for phosphorus. How do we know P is phosphorus?
Because we memorized it.
Because you memorized it. There becomes the nasty language. Yes, you have to know that phosphorus is P. Okay. Here, did we need to know it was phosphorus?
No, we could look.
I mean, we can look it up, but we're cheating. We don't have to actually know it because they didn't say phosphorus necessarily. They gave us the formula P. So we look at that P. We've got 15 and 31-ish. What do those numbers mean?
31 is the mass number and the 15 is the amount of protons.
Okay, so generally, I already forgot the numbers. On our periodic table, we have 40, I don't know where 40 came from, and 30.97, right? That's what our symbol looked like. What I'm asking is, what do those numbers mean? Okay, I heard the 15 is a mass number. No. Atomic number, yeah, it's an atomic number. Okay, but if you ask me, all you've gone through and used is another word to describe a location that means nothing to me. So what's an atomic number?
It references the number of protons and neutrons in the nucleus.
Okay, it references the number of protons and the neutrons as a sum? Or individually? Total, okay, sum together. You shook your head. Why are you shaking your head?
I thought the atomic number was just the proton, but it's not.
Yes. That's what I thought too. I thought it was just the protons.
The atomic number is just the protons. Okay, so where's the protons and the neutrons? The mass number. Cool, absolutely. The mass number, I give you 100% credit, yes. The mass number is the protons plus the neutrons. The number of protons plus the neutrons. Where's the mass number? Okay, so we've got a couple things floating out here. We heard someone say it's the top number. The top number was our atomic number. The 15 is just the number of protons. I had other people telling me, oh, it's the 30.97. Okay, when we talk about the mass number, it's the number of protons plus the number of neutrons. Which one of those counts is 0.97?
No, it's the top left, right?
The electrons.
Like the reference.
It's the electrons. What's the weight of an electron?
9.8 times 10 ×
1 over 1,827, the mass of a proton or neutron. Said another way, if I look at the mass of an electron in this structure, it gives me that place. Do I have enough electrons to even hit the scale for where my number's hitting? No. Why does it say 0.97?
Oh, because that's the weighted average.
Wherever that came from. Was that you? Okay. That's not the mass number. It's the atomic mass. Aren't those the same thing? No. They're very, very, very different, unfortunately. This is atomic mass. As an atomic mass, this is your weighted average. Remember that lecture video where you had to talk about isotopes and all that?
Yes.
Yeah, see, someone remembered. That was a deep sigh. Okay. Or in the lab, the FET assignment that you had to go through and deal with weighted averages, that's that number. So what is the mass number? The mass number is the number of protons and neutrons for an individual isotope. That's it. Okay? So I would have to very specifically reference that isotope. I can do that. There are some notations that bring that out, but that is separate from the atomic mass. Which means our periodic table gives us our atomic number and our atomic mass. And that's it. The atomic mass is related to the mass number. Why? The weighted average of what?
Every isotope's mass
Every isotope's mass number.
number.
Ballpark. Close enough. Yes. Okay. So the mass number does contribute to the atomic mass, but they are not one and the same. The atomic mass is a calculation of all the possible isotopes. Do you need to know what all the possible isotopes are? It's a good answer. No, you do not. So don't stress about knowing all of them. You're responsible for working with them once you are given them. Okay? So the mass number falls off for this, and we're now looking at our periodic table again. Okay, and the question, again, goes all the way back to what we were looking for, the number of electrons.
Isn't it the same as the atomic number?
Right? The atomic mass, we said, had virtually nothing to do with electrons, so that's off the table. How about the atomic number? That's the number of protons. When we're going through and building atomic structures, where we start is we assume an equal balance of protons and electrons, that it would be a neutral charge. So if we're trying to find the number of electrons for phosphorus, it is the same as the atomic number because we're making an assumption that they are equal. When would they not be equal?
When there's a negative or a positive sign.
If we put a charge on that particular atom. That's the only time. Where do we find information about charges? If I wanted to make this phosphorus here a -3, what do I got to do? Where do I specify the information about charge? Yeah, it has to do with electrons, but where is that information stored? Okay. Said another way, up here we would typically put our mass number. Down here we would have our atomic number. What do we put over here? This is the amount. Remember that 3? There it is, lower right-hand corner. Where do we specify information about our charge? Top right. That's where we'd see information about our charge. That charge is the balance of protons against electrons. Okay, against because they're opposites. Protons are positive, electrons are negative. Okay, so it's the balance against each other. So if I wanted that phosphorus to become a -3, what I need to do is specify a -3 next to it. What does that mean? It has an excess of electrons beyond its neutral. Okay? Which you'll deal with, but not quite this second, so let's not stress about that. So what does that mean? Phosphorus has 15 electrons. Okay? Is that my valence electrons? No. The valence electrons, as was suggested in the back of the class, is the outermost energy level electrons, which means I have to know where all of my electrons are located. Well, where are my protons and neutrons located? Nucleus, cool. So where are the electrons? Outside it. Everywhere outside it? No, not everywhere outside it. They're located at very distinct energy levels, or what we would call orbitals. Okay? Not to be confused with orbits. Okay? It's not solar system stuff. They're orbitals. Okay? So we would then need to go through and say, well, what are all the rules for how we place electrons into that? Okay? Well, some of those rules are embedded in our periodic table. So I've got 15 electrons I need to somehow put into phosphorus. So where I'm going to go is right back to my periodic table and say, well, what information is stashed within it? What can help me process all of this information? So when we look at the periodic table, not to scale, but close enough, right? Everybody see that? You see how the shapes match?
Yeah.
Cool. Can I come up with some labels?
Yes.
Cool. What labels can I come up with?
The orbitals that they fill.
Cool. The outermost orbital that's filled. These are known as the S. Why? Because sphere begins with S. And spheres look like circles. So when we draw that, that sounds good. That's an S. Okay? What's the next one?
D.
We might jump to D. And D's look like cloverleafs. Because cloverleaf in German begins with D. Does anybody speak German? Cool, you can just trust me on it. What's the next one? P. And that's because P looks like a dumbbell. In German, it begins with P. Why German? Someone's already calling BS. Why German?
The person that came up with it was German, maybe?
The vast majority of periodic table discoveries happen through Germany. Okay, we get a lot of discoveries through Germany and through Russia. Okay? So we can push back to German. Interestingly enough, we're probably now talking 80 years ago. Okay? To get a PhD in chemistry, you had to be fluent in German because all of the papers were written in German. So you had to be able to read German to get a PhD to pick up all of the content knowledge. Yeah, it's crazy. Okay? So cool, that's our dumbbell shape. What's the last one? F. You're like, what does that look like? It doesn't matter. Don't worry about it. It looks like a big interdimensional being. Okay? Why do we not worry about the F? Because nobody wants to fail. Thank you. Why do we not worry about the F?
Those ones are super radioactive, right?
Yeah. We're looking at the F block. The vast majority of those are radioactive, dangerous. You're never really going to be exposed to them because we like you. Okay? So we minimize your contact. So we can effectively delete the F block from our worrying, which then leaves us with the S, P, and D. So those are now the names of those blocks. Okay? Is there any other patterning that we could see within the periodic table?
The Roman numerals and stuff that show the balance level?
We'll come back to the Roman numerals.
Sorry.
We'll come back to the Roman numerals. Anybody play Battleship? I know it's an old school game. Yeah, a couple people play Battleship. Cool. So we could go through and say 4, 2. Let's do 4, 2. What am I talking about? Calcium. 4, we're talking about the rows down. Okay. 2, the columns across. We're talking about calcium. We can use that same strategy for this system. So if we start at hydrogen, where's hydrogen? 1. Okay, first column 1. In what block? So the very first electron for all elements is going to go into the exact same space. It's going to go into the exact same space that hydrogen has. So we'd go 1s, 1. Where's the next electron go? What's the next element? Helium. This one gets challenging. What row is helium in? 1.
8.
Yeah, weight becomes the weird thing. Okay? When we look at our table here, you will sometimes see hydrogen and helium floated off the table. Why are they floated off? Because they don't fit nicely. Officially, they're both S block. Okay? Which means helium is 1 S. Okay? And then we could say what column it is. We could say that too. Okay? But those superscripts now carry a different meaning. Those superscripts are saying how many electrons you placed there. So in the case of that helium, how many electrons did we place? Just 1. Okay? But I've now written the same thing twice. What could I do?
Sorry, 1s2.
I can condense 1s2. What comes after helium? Lithium, right? Hydrogen's 1, helium is 2, lithium is 3. Where's lithium? 2, the row. Still in the S. First column. Where's beryllium? 2s. Ooh, that looks like I'm repeating things, right? What comes next? We just did 4. Because we got 2 plus 2 gets us 4. What comes after beryllium? Boron. Where's that electron? 2. It's still in the second row. Is it in the S anymore? It's jumped, so it's now P. We could call that 1, but then we move to the next one, carbon. We would say 2P again. Nitrogen. 2P again. Oxygen, 2P. F, 2P. Ne, 2P. Or, thank you. 6. We've now filled out that whole row. Did we need to fill out that whole row? Have we gotten to phosphorus yet? Nope, so we have to keep going. What comes next? Sodium, yeah. What row? 3 in the S block. What comes next? Magnesium. Sodium's NA. Up one. It's okay. It's the angle. Okay? So 3S2, what comes next? 3, and we're jumping across now to P. So we can say 3P1 is aluminum, 3P2 is silicon, 3P3 is phosphorus for that row. What we now have is the electron configuration for phosphorus. Okay? If we did this right, all of those superscripts represent the number of electrons that phosphorus has. So 2 plus 2 is 4 plus 6, 10. What's the next one? 2. 12 plus 3, 15. And how many electrons did phosphorus have? Hallelujah, we've got our electron configuration for phosphorus. This tells us where all of the electrons are. Do I care about all of the electrons? No, what we're talking about is building a molecule. And as we build a molecule, the only thing that we first care about is the highest energy electrons. The ones that are furthest from the nucleus are the most likely to interact. So I want the highest energy level. Did we define an energy level yet? No. The answer would be no. As we say, no, Mike, no, we didn't define it. What were the rows? We just said there were rows, right? We just numbered them. Guess what the rows are? They're energy levels. Right? Why is that important for us? Well, if I want the valence electrons are the highest energy level. All I have to do is look at that first number. And I can say, where are my highest energy electrons? They're in the third energy level. How many electrons is that? 5. How many valence electrons does phosphorus have? 5. Now we'll come back to your lovely theory because we don't like doing all that work, right? Anybody like that? No? Okay, good. You still need to practice it. What's a better way?
If you look at the numerals, the Roman numerals and stuff, they're like the second digit of the 13, 14, 15, 16.
If you look at each of the columns, they have little titles along the top. Yeah, it's incredibly small. But if you look at the column title for phosphorus, it has a Roman numeral 5, and then it says A. A is a label. 5 is the Roman numeral. V is the Roman numeral. And V as a Roman numeral means 5. How many valence electrons did it have? 5. If we look at the number next to it, it says 15, right? How many elements are in the D block? How many columns are in the D block? 10. What happens when you subtract 10 from 15? 5. Your column tells you your valence electrons. However you want to interpret it, either through the Roman numeral or through the actual number written next to it. Okay? And what you're doing is ignoring the D block. Why are you ignoring the D block? This has to go back to common bonding patterns, and the common bonding patterns were based off of 8 electrons. Why 8 electrons? How many elements in the second row? 8. Everything was based off of octets. Okay, 8 electrons, which meant we ignored the d orbitals because they weren't there. Okay, so the numbering system also can subtract that out of the system. Kind of, sort of? Cool. So phosphorus, we had how many valence electrons? 5. So all that work, all that pain and suffering and misery, when we boil down to, did you just read the top of the column? Cool. So what's oxygen? 1s? Okay, cool. You already like, no, not doing it. Okay, we look for oxygen. The top of the column is 6. Chlorine, we look at the top of the column, it's 7. How many chlorines are there? 3. Does only one chlorine bring in electrons? Nope, all 3. Which means 21. I take 5, 6, and 21, and I got my number.
Wait, how did you guys get 6?
6? How did we get 6? 6 for oxygen is the column number. So you look to the very top of your periodic table, that number on top tells you your number of electrons underneath. Using the Roman numerals, it's explicit. Okay? We do have to realize the A, or if you look through the middle, you'll see B's. Those are secondary label systems. Those aren't part of the Roman numeral system. Okay? How did we get 7? We looked where chlorine was, top of that column, Roman numeral VII. That's 7. Okay? If we do that math, what do we come up with? 32. And you're saying that was marked wrong?
I think I got it mixed in because like I was looking at the electron, at the charges of it too, and like adding that to the.
Which brings in another whole issue is you could start to bring in charges. You say, well, phosphorus typically has a -3. Phosphorus has a -3 in an ionic compound. Did we define what ionic was yet? Nope. Which means, careful, you're starting to pull future information back, and the context in which you use that information is very, very important. All right, so we got 32 valence electrons. Does that mean we could build a Lewis structure now? Potentially. How many of you watched the video? 1 or 2 of you, I would suggest we not touch drawing the Lewis structure personally, but I will abide by the class decision. Do you all have other questions? I saw a hand first, and then I have no idea who I'm pointing at down there. I just heard sounds.
So that means that the column, that number on the top is valid for the whole column?
Yeah, isn't that neat? So if I want to know the valence electrons for iodine, iodine has 53 electrons. I could go through and look at its electron configuration and populate that all the way out. Actually, I probably couldn't now that I think about it. Okay, but it'd be really, really long and lots of electrons to account for. And at the end of that, I would go through and I would underline the highest energy level, and it's going to total to 7. I don't have to do anything with the electron configuration. Is it you?
Yes. So the S column, I don't really know, like what S, D, and P represent.
So the S, P, and D reference the orbital type. So that if we looked at the grid pattern and if we were at row 2, column 1, the shape of the orbital that holds the electron, we would call an S orbital. We could call it anything we wanted. We picked S.
So is S representing vertically the
First 2 columns. Anything in those first 2 columns, the very last electron, will be an S-type orbital.
and then D is the third column, like zinc,
Yep.
and then E is everything
Yep.
to the right of that?
And that's where recognizing those blocks becomes really, really powerful.
Thank you.
I was just gonna say, like, I was so hung up on I couldn't understand, like, the going back to, like, 3 when you're already on 4 and stuff, but the one, image that you had put on there of, like, the ziggy-zaggy thing, that, like, it clicked. I was like,
Oh,
okay,
God, I hate the
so
ziggy-zaggy thing. Should I draw the ziggy-zaggy thing?
Yes, that helped tremendously.
And we'll see why I hate the ziggy-zaggy thing. Mainly because I can't draw it very well. So the ziggy-zaggy thing that she's talking about, when we talk about filling electron orbitals. Okay, we're going to notice a couple things. We've got our numbers in front representing the energy level. The letter that comes after it is the orbital type. When we go up in energy, okay, from 1 to 2, we copy the orbital type and we add another. There's the P. We go up in energy to the 3rd, we have to copy everything underneath. So we get S and P, and we add another. Okay, so if we go up to 4, whoop, we must add another. And we go up to 5. We get 5S, 5P, 5D, 5F. This is usually where people get stumped. I think it's 5G. You'd be like, but there wasn't a G block. Yeah, why is there not a G block? It's too big. We haven't been able to build it. Okay? So now we'll attempt to zigzag through this. I'm not even sure I can pull off the zigzag. Which way do you zigzag? Did you draw it? I do it so horribly, which is why I don't like doing it.
Remember which one was on there. One sec. Oh.
Oh, so you go this, 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 this. And you might be like, what the hell? I know I am. So we go up 1S, 2S, 2P, 3S. What comes next? So there's our 3S curling back, and then we go back up. 3P. What do we expect to encounter after 3P? You don't expect to see 3D. Isn't D the next one?
After 4S.
It is. But interestingly, we fill 4S first before we then fill the 3D. Okay? So we go up in energy and come down in energy. That seems a little bit weird. Okay? How would we ever know that without the zigzag thing? Because the periodic table freaking tells you. Okay? Where's your transition? That 3P to 4S. 3P ends us at what element? Uh, 3P max, 3P6. What element are we at? Third row, P block, sixth column.
30? Is it S?
Okay. And we should be at AR. Hopefully we know AR is argon. So we'll walk through. It's maybe a little high for me to be able to point. And by maybe, oh no, it's good. Okay. 1, 2, 3, and then we said 6. So 1, 2, 3, 4, 5, 6. We're at argon. Okay, what comes after argon? What comes after 18? 19. What comes after argon? Potassium. Where's potassium? It's in the fourth energy and the S block. The periodic table told me that information. I knew I needed to fill the 4S before the 3D because the periodic table is organized that way. But now we do encounter an issue within the periodic table. Calcium is 4S2. Scandium is D. Cool. Which row? Be like, well, it's in the fourth row. The D block is offset by 1, which means it's actually 3D. Hooray! It's also one of the reasons why I don't like this periodic table. I like to actually see sections. I would like to see a white gap in there, and I would like to see a white gap over here, so that you can see that those are kind of separated out, and that helps for that flow. Same deal with the hydrogen and helium. I like to see them floated off the table a little bit because they do weird chemistry that technically abides by both the P block and the S block. Do you care? Probably not. Don't worry about it. Just follow your patterns and you're okay. Was that your question?
No,
Where did that question come from?
Just doing it because he had confusion with like that.
Oh, you wanted the zigzag thing. Oh, God, yeah. Okay, and there's the zigzag thing. Okay. Why did I screw it up? I have no idea which direction I'm supposed to go at once I've got it written out, and I'm not very good at straight lines nor grid patterns. And you have to have both of those nailed down pretty perfectly to use the system. I'm a little too crooked to figure that out. Thanks for the smile. Make sense? What next? Say again?
Why the last column for the helium, what is the value for that?
For the helium? So the main reason why I want them floated off the periodic table has to do with kind of where these names came from for each of your orbitals and all that fun stuff. And when we go through and look at how these things come about, okay, so slight sidetrack. When Marvel realizes they've killed too many of their characters and they're like, oh crap, we wanted those characters back, what do they have to do?
Bring them back.
How do they bring them back?
Multiverse
Why can they go to the multiverse?
magic.
Close. They use a different word. Quantum. And as soon as you drop quantum on it, everything can happen. Where those numbers are coming from is ultimately solving for the location of an electron in these individual systems. And when we try to figure out where the electron is located, there's a bunch of variables that control it. Right? Those variables end up being these numbers. Okay? And if we look at the first energy level, there's only one space it can be, the s orbital. There's no other space. Okay? So it's a repercussion of solving those quantum equations, which are amazing and beautiful, but you're like 3 years from that class. Okay? So if we want to know what's going on with that helium, this is where I sometimes like to see helium drawn here. And we'll touch on the other part in a second, putting the hydrogen drawn next to it. Because if you put them in those spots, it helps to signal some of that information. So for instance, by placing them here, this signals the electron configuration for helium. Because helium is S block, so it should be in that S block, and it's the second row, so this should be 1s2 for helium. Why do I want hydrogen on the other side? Because hydrogen has the ability to react very similarly as an element as if it was next to helium. So this red and the blue are kind of representative of both their electron configuration on the red side and the blue side, the phantom chemistry, if you will, of that atom. Okay? And it helps to signal both those pieces. Probably the best version I've ever seen is that we do something like this. We don't put them in any columns. We just float them entirely off the periodic table and just say this is S. Deal with it. Okay, and officially it's 1s because it's the first row still. Okay, does that kind of touch on your answer in a dodgy sort of way? Next question. My turn. Karen, what number was it? I don't know, it's fine. I can scroll. Oop, there it is. That's as big as you'll go, huh? Okay. This kind of touches on the paper homework. So, at least one person, probably multiple, went through for the paper homework and they went through and said, what is mass number? And they said it's protons plus neutrons. And then if they did a really, really good job, they said page 62. So they referenced where that information was found. Good job. Okay. They might have also said where are protons and neutrons? They are in the nucleus. Page probably earlier. Let's go with 53. the record, please don't reference those pages. Those are made up numbers, I'm guessing. Okay, and then what is the mass of protons, neutrons, and electrons? So respectively, 1, 1, 0. We'll call that page 53 also. Okay? So they came up with 3 questions. These 3 questions are absolutely true as far as statements. I'll give you credit for that. You've cited the information. You've provided the context. I'm okay with that. However, what you're now assuming is that when you move into an exam, what you're going to get is a definition question. That was a bad assumption, and you've now shafted yourself because you had an opportunity to get practice to try and dig deeper and apply these concepts. And instead of trying to apply those concepts to more challenging questions, what you went through and did was selected the easiest possible things you could get to get points. You've gotten your 10 points for the paper homework, but you've now eaten tens of percentages on an exam. That's the problem. Okay? Because those 3 questions are information that's needed to answer question 16. You now have all of the information to answer it. Work together. Right now. Figure it out. What is the answer to 16? So let's try it this way. What do we think the answer is?
A.
Okay, so we're getting a little bit of a mix here. Okay? This really heavily requires applying all of the knowledge you've got. Okay? So let's go through and let's pick B. Sulfur 32. What does that mean? If I say sulfur 32, what information does that give me?
32 number is the mass number, the number of protons and neutrons.
There's not an E in sulfur. So this is the protons and neutrons. Cool. Does saying sulfur give me any information?
Number of protons.
Yes. You could go to the periodic table and see all the information on there.
So the periodic table, sulfur, should be able to tell me what? It tells me the number of protons. It does give me the atomic mass. Do I care? What is the atomic mass? What is the meaning of atomic mass?
The weighted average.
The weighted average of
All the isotopes.
all the isotopes. We're looking at a specific isotope. The weighted average doesn't really give me a whole lot here. Okay? What we're asking is it allowed? Am I allowed to have a sulfur 32?
Probably not.
Okay? So why not? What was the weighted average?
Okay, yes. I meant to say yes. Because I said the answer was A.
Okay? The weighted average was 32, which would suggest 16 protons and 16 neutrons. If you go through the process of looking at how protons and neutrons equate, it's roughly a 1-to-1 ratio. Okay? So we need neutrons to balance out the protons. Why? Because there is an exception to that. There's a huge glaring exception to the ratio of protons to neutrons. Anybody know which element?
Hydrogen.
It's hydrogen. How many protons does hydrogen have? 1. What's its mass? Its average is effectively 1, saying that hydrogen does not need any neutrons. But when I add 1 more proton and I move to helium, what happens? I compare the atomic number to the average mass. The average mass is significantly larger. Take a look at all of your elements, and you will note the average mass is significantly larger than the atomic number. Every single time. Why? What is so different about hydrogen versus every other element?
It's a single proton.
Hydrogen only has one proton. When I move to helium, I add another proton. And what do those positively charged particles do when they get near each other?
Propel.
They repel. How do I fix that repulsion?
Electron.
That's the point of neutrons. Neutrons act as the glue to hold your protons together. So if I go through and look at sulfur, if I have 16 protons, does it make sense that I would have 16 neutrons? That kind of hits that golden ratio. Kind of makes sense. Right? Nobody said phosphorus, so should we ignore phosphorus? Yes, okay. And we move to germanium. What does that 32 mean? This is the protons plus the neutrons. What does the word germanium mean? "32 protons. How many neutrons do I have in germanium 32?
None.
I have 0. What happens when I bring a proton near a proton? They repel away. Can I have germanium 32? No, that atom would literally explode apart. So which one's not physically possible? Germanium. Why? We're interpreting our mass number. We're understanding what the mass number means. We understand what our protons and neutrons are, where they're located, what their purpose is in each of those systems, what their masses are. And we now have to stack all of that information together to come up with a solid hypothesis for why germanium 32 should be wrong. Are there other ways this question can be formatted? Yes, there's actually a lot. It's a fun question. I like it a lot. Subtle hint. Yes, sir.
Okay, I think I did it wrong, but I got it right. The way I thought, well, this is wrong, I already know now, but the atomic mass, I saw in isotopes, it's pretty dang close to the atomic, or the atomic mass is close to the number that comes after the element. So the way I just did, I was like, okay, well, sulfur has 32, phosphorus has 31, so there's probably an isotope that has 32, making it possible, so germanium can't be possible.
Yeah, so what you're encountering is the right answer for the wrong reason. On the exam, do you care?
On the exam, no.
Good. Okay. You don't have to be perfect all the way through. Okay. But you will encounter questions that will break your brain a little bit or bend it.
So should I
Okay.
be worried about that and not do that ever again?
Should you learn the content so that you always know the content? Yeah. What do you want me to say? No, just get lucky every time? Okay. So the odds that you get lucky every time are slim. Okay. So you should learn the content. You will have gaps, which does come back to exams. What is the point of the exam?
Should get it right.
Okay. Your point is to get it right. What is my point? I want to test your knowledge. I want to push to see where you don't know. Because that's what an exam does. If you take your car into the mechanic and be like, it's not working very well, and they kick the tires and go, the tires are full, it should be fine, you're probably not going to go back to the mechanic. Okay? You need them to run the diagnostic to figure out what's wrong. You need them to take an exam on the car to find the problem. That's exactly what a test should go through and do. That is probably a 180 spin from every exam you've ever taken. Okay? Most exams, in my experience, at least within this state, have been written to make people feel better about learning. That's not the point of an exam. The point of the exam is to figure out what you don't know. Because once we figure out what you don't know, what can we do? We can make sure you learn it. Okay? That's the point. Okay? Ideally, we figure out what you don't know before the exam, which is why you do practice. That's why you do the homeworks. That's why you find questions that you can't answer and figure out why you can't answer them, so that when the exam rolls around, you've already figured out what you don't know, and it's nothing. I think I said that right. That was a good way to say that. Okay? And now, yeah, the exam is easy for you. Okay? And that means what do? We move on to the next section of content and we try to break you again. Right? And it's not breaking, it's a learning process. That's the point. Kind of, sort of? Okay. So, be careful with your paper homeworks. Make sure that what you're doing is probably a step beyond just definitions. If you're going to do definitions, that's okay. Cite pages. Dirty secret, I'm not checking. I might eyeball it. Okay, if you're telling me you found it on page 2 and it's talking about how to do mole conversions, I'm like, no, okay. Now you're telling me I have to grade your work, thanks. Okay? But the point behind that is checking your work to be like, how do I actually know what I'm going through and doing? You're trying to find your weaknesses, not me. Kind of, sort of? Do you want a different exam question? Or wait.
I have a quick question. For the exam, do we get, like, on the practice form, do we get a page of the periodic table, or are we representing the table?
Nope, you'll get what, I think this one has it all in it.
Yeah, this one has it on the first or second page.
The very first page will look something along these lines. You've got that as your heading, and then you've got the directions. Okay? Instructions are important, y'all, just for the record. And if you haven't spent the time, you might spend a hot second. Then you'll get some conversion factors, and you'll get that periodic table. Those are on the flip. I would actually recommend you tear the first page off and flip it over so that you can see this the whole time you take the test. Okay, because it's a waste of time to get halfway into the test and be like, oh, I need the periodic table. Where was that? No. It's right here in front of me. That's where it is. I would argue even further. Did you memorize any stuff that you're like, oh, I really need to know this in case it shows up? Right? If you're one of those people that was trying to cram that information in, that's okay. Don't wait for it to show up. Word vomit it on that page so that it's now in front of you. So when you do need it, it was there at its most likely point to be correct. Because if you wait till it shows up in the exam, you've now lost track of that information and you could easily have swapped it around. Kind of, sort of?
Why do some elements have the X in the top left and then 0 in the top left?
Okay, which elements have an X?
Nitrogen, oxygen.
Do you notice a pattern? It's kind of small, I know.
No.
The ones that have an X are all what color? Okay, that's fun. Orange, I would call it red. I see you. Okay. They're all red. The ones that have O's are blue. What does red, black, and blue mean up there? Yeah, if you're like, I can't see it. I know. That's why you have this periodic table that tells you at the bottom, X means it's a gas. O is liquid. And no extra information is that it's a solid. So it gives you the phase of matter, the standard state. So that's why those letters are there.
I don't know if we've gotten this far. I think we have. But number 22, because I think it's about like finding like public communication.
Should have told you to look away while I scrolled. Sorry. This is a gray area based off conversations I had with you. Okay. So things that you do know at this point. What are you responsible for knowing? That I'm fairly certain has been covered. The groups. Your alkali metals start with, depends how you want to label it, hydrogen or lithium. I'd accept hydrogen, we'll stick with that. Our halogens are? Oh, the halogens are F for phosphorus because phosphorus begins with P. F is fluorine. This becomes that challenge on trying to memorize them. It's quite all right. The alkaline earth, beryllium, noble gases, helium. The carbanogens, I can't believe that's on here. The carbanogens I completely made up. So some of the things, by the way, that I've gone through with training is in building multiple choice exams, 5 answer choices is actually useless. You should really only have 4. I'm not universal at doing that yet, but I'm getting better about it. So because usually what it comes down to is you need distractors. Well, is anybody going to write carbanogen as an answer? The number of people that select that are like, that just sounds stupid, I wouldn't pick that. And it doesn't get used. Well, if it's not used as a distractor, that wasn't a useful distractor answer. So delete it. So, yeah. The oxygen, for the record, chalcogens is the oxygens. And the nitrogen are pnictogens. You don't need to know those, I just think they're fun. Okay? But these ones you are responsible for knowing. Okay? So that gives us information about where they're at on the periodic table, so that's cool. Okay? But then it falls in with this predictable ionic charge of 2 positive. What does it mean to be 2 positive? That's Mike about everybody's success in the class. Okay, so we heard 2 things. We were gaining 2 protons, or we were losing 2 electrons. What happens if we gain 2 protons? What would happen to our charge? What would happen if we gained 2 protons? What would happen to the charge? It would increase positivity. So that absolutely makes sense in that respect, except by increasing the number of protons, what did you do to the identity of the element? You've changed the identity of the element. Okay? And when we're talking about ionic charges, you're not changing the identity of the element. Okay? The only thing we're allowed to play with and touch are our electrons, which becomes challenging because how can I become positive if I'm adding negatives? It's because you're not adding negatives, you're subtracting it. You mean you're taking a negative of a negative, also known as a positive. Negative signs are going to be a recurring pain in the butt for the rest of your careers ever. Just look at your bank account. Okay? So pay attention to them. They are challenging to nuance. So we're talking about something losing 2 electrons. Okay? If we looked at hydrogen, would hydrogen be a good example of losing 2 electrons? That's going to be real questionable. It only has 1 electron to lose. But what we're talking about is that entire family, which is why I would not use hydrogen, and I would use instead lithium. Okay? So if I looked at answer choice A, I'm talking about lithium. Lithium losing electrons, we would look at 1s2, 2s1. If I lost 2 electrons, what would I look like? 1s1. Okay? So in all of those cases, I'd end up going down to a half-filled orbital, an s1. What if I move to the halogens? Okay, we can look at fluorine. 1s2, 2s2, 2p, 5. If I lose 2 electrons, what happens? (2p3). Why are we doing all this? I'm not seeing the pattern yet. That's okay. C. Take a look at beryllium. 1s2, 2s2. What happens? Some people just shook their head yes. Why'd you shake your head yes? Oh, just that? Okay, cool. That's fine. D, noble gases. Helium, again, is a little bit weird because of where it's at, so we could drop to our neon. 1s2, 2s2, 2p6. If it loses 2 electrons, what does it become? Anything stand out? No was a perfectly acceptable answer. And I believe this was your question in the back, right? All right. Does anything stand out to you?
The energy level, like the valence electrons, and
So the amount of energy levels is going to be ultimately arbitrary depending on which element we picked. So we got to be careful with that.
The valence electrons is 2.
What about it being 2 is special?
Because 2 represents the amount of electrons, and it started off with 4, and so 4 minus 2 electrons is 2.
And 6 minus 2 is 4.
And 6 minus 2 is 4.
Yeah. Why is it relevant?
So there's a positive charge
Because
of
you're
2.
making it more positive.
All of these are being made more positive.
Only one of them has a positive charge of 2.
More positive by 2.
All of these have a positive charge of 2. Which one of these is better as a positive charge of 2 becomes the question. What is the s orbital? First, how many electrons can we fit into the s orbitals?
It's complete and brilliant,
2.
so it's the most happy.
If we move to the p orbitals with our dumbbell, how many electrons can we fit into those? And figuring that out, count your columns within the p block. 6. We could look at the D and F, except in these scenarios, we aren't going to need to get to D and F. All we're going to look at is S and P. If we look at answer choice A, how many electrons are in our s orbital? 1. Is it full? No. What happens when we move to B? Not full. We move to C.
Yes.
Ooh, it's full. We move to D. Not full. So if we go through and look at these, not. What do you think your answer is?
C.
Which one of these things is not like the other? But why? Everything likes symmetry. Think of the most beautiful person you know, or handsome, however you want to look at it. Okay? And studies have shown they're symmetric. Okay? So the more symmetric our systems are, the more stable they become. A fully filled orbital is more stable than a half-filled orbital. So you can use electron configurations to predict these. Could you do something else? Yeah. Pull out the periodic table. Top of the column it says hydrogen. You would write +1. Column it says beryllium. Top of that you would write +2. Top of the column that says N for nitrogen, you write -3. Oxygen, -2. Fluorine, -1. Those would be the common charges. Where did they come from? Electron configurations. You can predict those from your electron configurations if you so choose. You don't need to, though. But I wanted to bring it back to something that you have control of. You should know your electron configurations. With that, we're done. If you got lab scheduled for today,